Welcome to part 3 of overview of exponential and log functions. I know there's a lot here. Normally we spend a whole week on this concept, and we're trying to summarize. I'm trying to summarize it for you all as briefly as I can, but there's just a lot of material to cover. So if you go through the Alex Pie, they start you here, the fundamental properties of logarithms. I'm not sure why they choose this as a starting point. It's the least connected to applications that you can get, but this is where they start. In order to solve more complicated problems involving exponential and log functions, you need to have the properties of logs firmly under your belt. These are also called the laws of logs, which I like better. It flows better. So again, remember, these are how the two exponential and logarithmic functions are connected. Now, logs were developed in the first place so that you could turn a complicated multiplication problem into an addition problem. If you think about it, I want you to think a little bit about exponents. If you take something like, let's see, like if I take 2 squared and I multiply that times 2 cubed, what do we do with the exponents if I'm taking two things to the same base? Well, I know this is 2 to the 5th, right? So I'm multiplying 2 5 times. 2 times 2 times 2 times 2 times 2. But what am I doing to the exponents? The exponents are getting added. So since logs give you powers, I'm caring about the powers of these 2's, so I care about the addition problem. So it takes complicated problems where the base is not so simple, like the base might be 1.157, and it turns it into a much easier problem because I'm only focusing on the exponents. That's a very, very brief description. Okay, so we're going to use this fundamental definition of logs to just explain why this is true. Now, if you don't care about the explanation, just fast forward through the video and memorize these, but I like to explain why. If I convert, remember, the base raised to what power is equal to the argument. So if the base and the argument match, it has to be the first power. B raised to the first power must give us B. So anytime the base and the argument match, the answer is always 1. So if I say, what is log base 4 of 4? I know that. It's just 1. And what is the natural log of E? Again, I know that. It is 1. That one's really important. That comes up all the time. The natural log of E is 1 because the base and the argument match. The next one, the base raised to what power equals 1. Anything raised to the 0 power equals 1. So anytime the argument is 1, your answer is going to be 0. Anytime the argument is 1, the answer is going to be 0. So if I say, what is the log base 4 of 1? You say 0. If I say, what is the natural log of 1? You say 0. Again, this one comes up all the time, and so does the natural log of E. Those two are probably by far the ones you use the most out of all of these. Next, the base raised to what power gives us that same base raised to the same power, right? So this one's a little bit confusing because I have these b to the x and b to the x, but let's look at it in a more straightforward way. If I ask you to find the natural log of E raised to the 7th power, remember, a natural log is base E, so E raised to what power gives us E to the 7th power? 7. E to the 7th power gives us E to the 7th power. So this is always going to be 7. You wouldn't say, oh, natural log of E is 1. 1 times 7 is 1 to the 7th power is 1. You would not do that. Okay? Lastly, this one at the bottom is used in very few cases, especially at this level, and not something I focus on at all. I don't believe Alex even covers it. But sometimes a way to solve an equation is to raise the whole equation up to a power, and that's when you use this property. If I have a base and it's raised to a log, and the base in the log matches the base here, then my answer is going to be the x. Because, again, this one is a little bit confusing. You're converting this one to a log. So log base b of x is equal to log base b x. So what happens is you see something like this. You have a 7, and then you have a log base 7. And I want to know what my answer is. My answer is the argument 2. Again, this is not used very often, not at all in this course really, but it's something I wanted to expose you to, and if you'd like to memorize it for future use, feel free. So this is the properties sheet that I have in the Google Drive for you. You need to print it out and make notes on it so that you remember it. I'm going to go through the explanations on why these are true. Again, if you don't care about the explanations and you prefer just to memorize, you can do that. I remember things better when I know the explanation. Just fast forward through the video if you don't want to see the explanation. Okay, so remember, logs give us powers. So if I think about 2 cubed times 2 to the 5th, that equals 2 to the 8th. I'm adding the exponents. So if I think about this in a log problem, 2 cubed is the same as 8. 2 to the 5th is the same as 32. So log base 2 of 8 and 32, 8 times 32, is the same as log base 2 of 8 plus log base 2 of 32. So what happens here, what I'm really saying, let me make my pointer white so you can really see it. I'm saying if I have a single log and it's got multiplication inside the log, this circle is not working, multiplication inside the log, then I turn it into 2 separate logs with addition. Okay, they both have their 2 separate logs with addition. Or if I have 2 separate logs with addition, I can turn that into a single log with multiplication in the argument. Goes either direction. Same thing with our quotient rule for exponents. I know that division equates to subtraction. So if I have a single log with division in the argument, I can turn that into 2 logs with subtraction. The last one is the one we use the most. If I have a power raised to a power, that becomes a multiplication problem. So I have a log with the argument raised to a power. I can move the power to the front, and it becomes a coefficient. It becomes a multiplication problem. Similarly, remember this goes both ways. This we use more often. If I have a coefficient on a log, I can move it into the exponent on the argument. All right, so let's just do a little bit of practice rewriting. Again, this is the first topic you encounter in logarithms, in the exponential and logarithms section of ALEKS. So if I want to rewrite this as a single term, I can't have any coefficients. This 2 cannot be in front, and they all have to be the same base, natural log, natural log. If they're not the same base, I can't do it. So the first thing I have to do is move the 2 into the exponent. So I get natural log of x squared plus the natural log of x plus 6. Now, I know from my properties, if I have 2 separate natural logs with addition in between them, I can turn them into a single natural log with multiplication. So this is x squared times x plus 6. Sometimes you're required to simplify. If you can, this can't be simplified, so I'll leave it. Now the next one, I don't have any coefficients. I have 2 separate logs and subtraction. 2 separate logs and subtraction says, from my properties, I know how to do this. I can create a single log with division. And it's the same base, log base 5. And now I have a division problem. So the numerator is x squared minus 4, and the denominator is x plus 2. Now here is one where I would expect you to simplify it, because you know that you can factor the numerator. The numerator, I still have my log, base 5. The numerator becomes x plus 2, x minus 2. And the denominator becomes x plus 2. Now why did I bother doing that? I did that so that I could cancel the x plus 2's. So I get a much simpler answer. My answer is simply log base 5 of x minus 2. So that is writing it as a single log. Now you might say, wait, there's subtraction. No, this is inside a single logarithm. It's only when you have subtraction between two separate logarithms that you change it. Okay, here, this one is, you say, what do I even need to do with this? Well, if I ask you to rewrite it, you don't ever leave an exponent in your answer. So an exponent in the argument, it always needs to come to the front as a coefficient. So this is x plus 3 in parentheses, and then the natural log of 5e. Now, this I could actually do some more work on, because here I have 5 times e inside of a natural log. So this is the same, let me get this, as x plus 3 times the natural log of 5 plus the natural log of e. Remember what the natural log of e is? Hopefully, anything raised to the first power gives us that thing based on the argument match. That's 1. So I could write this as two binomials, which I'd have to FOIL if I wanted to write it out without parentheses. So we'll just leave it natural log of 5 plus 1. Okay, now here I want to rewrite as a sum or difference. So here I have multiplication and division, so I'm going to separate the division first. So this is the log of x squared z minus, because it's division, log y. And then I'm going to split up the log of x squared z. So since it's multiplication, it becomes addition. So I get the log of x squared plus the log of z minus the log of y. Now there's one more thing I have to do. I have to move the 2 to the front. So finally, I get 2 log x plus log z minus log y. So that is expanded as a sum or difference of simple log terms. So no exponents on our arguments, and everything is expanded out. This one, remember, a square root is actually an exponent. It's, what is it? It's raised to the 1/2. Oops, 1/2. So this is the same as x over x plus 5 to the 1/2. So I need to move the 1/2 to the front. And then this division is subtraction. So I have 1/2, and then both of them were raised to that power. So I need to make sure that in my answer, they both have that coefficient. So I put them in brackets, like that. Now, this is as far as you can go. If you want, you can distribute the 1/2 and write it without brackets, but that's it. Solving exponential equations with logs and the other way around. There are 3 methods to solve. We're going to actually save this for part 4.